A very good morning to one and all. My name is Paraniappan Ramu. I am from the Department of Engineering Design. I work on optimization and treatment of uncertainties. The course that I am going to instruct now is Surrogates and Approximations in Engineering Design. In the context of engineering optimization, usually we do not have the objective function or the constraint or both of them in explicit form. In such cases, people usually use an approximation or a surrogate. A surrogate is also referred to as a meta model to represent the objective function or the constraint and perform the optimization. This course is about such approximations or surrogates or meta models. The question is how to build them, how to visualize them and how to use them. Finally, how to infer the results that are an output of such a formulation. Now, if we step one step backward and look at a classical optimization formulation, we usually have a minimization or a maximization problem of an objective function. Usually in a classroom setup, we have a closed form function of some f of x where x could be a vector. So, the idea here is that f is known subject to some constraints, which is again depending on whether it is an equality constraint or an inequality constraint. We use the notations usually g I and g h, where I runs from 1 to n, and h j where h refers to the equality constraint and j runs from 1 to m, where m is the number of equality constraint and n is the number of inequality constraints. But oftentimes in real life problems, for instance take a car crash example, the usual objective function is you want to make sure the occupant is safe. One of the criteria or the metric that is used for that is the head injury criteria. So, you want to minimize the head injury criteria or the impact to the occupant subject to some constraints, let us say weight, or this formulation can also be swapped. I want to minimize weight such that the head injury criteria satisfy a particular constraint. Weight could be formulated just like a summation of a linear sum of the weight of the components that you are looking at. But the head injury criteria need not have an explicit form or an equation for that. In such cases, we depend on a finite element simulation or some kind of a digital twin, that is the word that is usually used these days, which will actually give you the head injury criteria for some combination of the input variables. So, you want to build a surface of this head injury criteria, which is again a representation of that function, and use this meta model or the surrogate in your optimization formulation. So, the question now is how do we go about building these approximates? Okay. So, usually you cannot get as many samples as you want. So, you first design upon a design space, and based on few samples on the design space, you run these expensive simulations or experiments. For instance, the car crash example, it is very expensive to do an actual car crash. It is going to cost you almost the cost of a car to crash a car, right. So, it is very expensive. So, you seek the help of a finite element simulation or a computer model and simulate the same crash. So, you take those values at only few points in the design space, and now you want to fit a surface to it. The moment I showed like this, I am also trying to tell you that the function itself could be non-linear. It need not be a linear surface, it could also be a non-linear surface. Then the number of samples that is required to approximate that non-linear surface is going to be more. So, these are the questions that we will try to answer part of this course. Just to give you an idea, let us say in 2 dimensions, because the moment we are greater than 2 dimension, visualization is not straightforward. So, let us say that this is going to be the surface, this could be as simple as your weight. the weight is nothing but a linear sum of the components that you look at. So, if you are looking at this as x1 and this as x2, then this is a linear surface. So, it is fairly straightforward. Okay. So, you could, if you are just looking at a projection which is a line, I would just require 2 points to connect that line. So, maybe with as limited samples as 3 or 4, I might be able to construct this surface. Okay. It is a linear surface whichever way it is, okay, whether it is a constant line, whether it is like this or it is like this. If an engineer expects the surface to be linear, then you need very less samples in 2 dimensions, and so is the case for n dimensions as well. Okay. However, now let us say the surface was not like that, but it was something of like this, which is probably a cubic or a quadratic function. Okay. The point to be noted is we do not know what is the order of this function a priori. If you know the order of this function a priori, half of the job is done. Okay. Oftentimes we do not know, we just know that it is likely to be linear, it is likely to be non-linear, but you do not know what is the order of the non-linearity. Is it 10th order or is it 2nd order or is it 3rd order, we do not know. Okay. So, if it is just like this, probably I will require about 6 to 8 points to approximate this function. However, if this function is highly nonlinear like this, then I do not know how many samples I will require, but please understand this approximation of this surface is only going to depend on the number of points that you have, okay, and the location of these points. There is no point in having too many points in a cluster, okay, in a close by cluster. Okay. They should be across the word that is used across the design space. The word that is used is exploration and exploitation. The entire design space need to be explored. So, now there are several steps in trying to do this. The first step is sampling. Given a design space, meaning I just know only the limits of the design variables. I know the lower bound and upper bound of all the design variables that I care about. That defines my design space. The moment the design space is decided, now I need to decide where I am going to run my simulation or my physical experiment. I cannot run it across all the possible points, which is I do not know, few million. I need to do, maybe I have a budget constraint, either it could be a computational budget or it could be a monetary budget. I have to run it only at few points across this design space. So, the first question is, where do I run these n experiments? Okay. There are multiple ways of looking at it, that is where design of experiments come into picture. So, we will briefly discuss that in this course, the underlying idea about design of experiments. We will talk about simple design of experiments like the orthogonal array, the Latin hypercube sampling, which is very widely used in automotive, aerospace and biomedical industry. And then we will also talk about Hammersley sequence, which is a pseudo random number generator. Such design of experiments we will talk. These are predominantly come from a statistical background. Okay. The idea of the design of experiments would be to explore the design space to the maximum, Once we have the design of experiments points, we are going to go run the simulation or conduct the experiments and we will have a response. The moment you have the response, the job is very clear. Okay. What you need to do is you need to relate the response with respect to the input variables. That is what y equals f of x is what the original function is, but now you are going to approximate this f that we refer as f hat. This f hat is what the meta model or the surrogate is. Okay. Since it is not the model itself, it is a meta model or surrogate, it is not the real function, it is a surrogate function. So, we usually write it as y hat equals f hat, because y hat is an approximated response, it is not the actual response, equals f hat, and then you write y equals f hat plus some error. Okay. So, you need to have this modeling perspective to begin with. So, now we have some y's, some x's, we need to construct this f. There are multiple ways of looking at it. The most simplest way of looking at that is a regression model. All of you would have done curve fitting or line fitting. just a higher version of that is what surface fitting is. The moment your dimensions are greater than 2, then it becomes a surface. So, the same idea of regression, which is a minimum least square, can be used for modeling a surface. That is what we usually refer to a polynomial response surface. It is a surface of the responses. So, it is a response surface. Since you are using a polynomial to represent that surface, it is called a polynomial response surface. But of late there are also some advanced techniques like kriging, support vector machines based regressions. So, we will discuss such techniques here, radial basis function, and I will also touch upon some very latest techniques on machine learning, such as ADA boost or random forest, which are essentially classifiers, but they can also be used for prediction. So, we will be discussing such techniques. So, once your f hat is ready, then for any new combination of x's, you can find your y using this f hat. The point that you will have to remember is the y that you get out of this f hat is only a y hat, and there is always an error that is associated with it. So, one needs to understand how to account for these errors, number one, because we recognize that these errors are there. How to account for these errors, what are the error metrics that one need to account for, so that what is the confidence that I have on the prediction that I will get out of this f hat. So, we will be discussing such error metrics, how to use these error metrics to infer the results that we get out of an optimizer. So, just stepping a few steps backwards, the moment you have these functions approximations as f hat or g hat or h hat, they can be plugged back into our optimization formulation, and we can go about using any of the existing optimization techniques like any of the gradient techniques or the heuristic algorithms. Okay. It could be the sequential quadratic programming, or you could use a genetic algorithm in NSGA toolbox. The only point is this course will enable you to build these approximate functions from expensive computer or physical experiments, so that these functions can be used in the place of the objective functions or the constraint functions and facilitate an optimization. And the optimization algorithm could be any of the existing optimization algorithm, depending on the applications you are looking at and depending on the output that you are looking at. So, essentially these will be the topics that we will discuss. We will touch upon an introduction to optimization first. We will say why, what is the necessity of the function. Then we will talk about expensive computer simulations or physical experiments, why we need a meta model or a surrogate modeling approach. Then we will go about constructing the meta models themselves. So, we will talk about the design of experiments to begin with. Then we will talk about building the meta models. Then we will talk about evaluating the meta models using the error metrics. Then finally, we will touch upon a little bit on the visualizations, because usually the trouble is greater than 2 dimensions we are not able to visualize. So, what are the different ways in which we can visualize. So, these are the topics that we will talk about. So, though the meta model context is set up on the engineering optimization, these approximations can be used without an optimization background as well. For instance, now for the design space exploration, oftentimes people do not want an optimal result, they just want to understand how a function looks like. Okay. In my design space, what are the zones of interest, they want to understand that. So, these approximation techniques can be used for such purposes as well. So, that is going to be the idea of this course, and as I pointed out, the topics that I mentioned a while ago will be covered as part of this. Okay. We will have regular assignments, and there will be quizzes as well. This is going to be a 4-week course with about 10 lectures, I guess. If possible, I will try to bring in experts from the industry. There are a lot of industry collaborators who work with us on a co-design idea. There are automotive companies, and there are aerospace companies and biomedical companies, to name a few, who are interested in these kind of meta models or surrogate based optimization. Of late, all the commercial final element softwares have a response surface tool, which is essentially the meta model based tools, and in the academic community this is usually referred to surrogates or meta models. So, yeah, that is pretty much it, and I hope this will interest you and you will enroll for this course. I look forward to see you guys in the course. Thank you.